start recording so I don't forget that at least. So, like I said, your assignments suffered a mocha blow, but I increased your mark by one mark on Moodle, so I'm sorry. Anyways, yeah. So make sure that that's done on Moodle. Does anyone need the chapter 3 notes? Remember, we're going back to 3.4 today for the binomial. Fun, right? I know. Little recap. Well, we didn't go through it, but if you wanted to for the first test, right, you had the option of, was it on the test? Yeah, you could do it for bonus, right? So you might have looked it over already. I do. They're full. All right. So, yeah, it feels like so long ago that we were in chapter 3. That's where we first started introducing the z-score and the z-table, and then we kind of deviated, or we were meant to deviate into the binomial, which is actually going to be easier to deal with now than it would have been then, because you've seen hypothesis testing for proportions. Oh, here, Carly. So today, I almost put 2017. That's bad news, right? Yikes. So today, we're going to go back and cover the binomial officially, even though I think a lot of you kind of went through it on your own, right? But I'm not going to assume that. And it was a while ago. And the only reason that I want to go through it again is just because it's on the final. Yeah. Oh, yeah. It was me being cheap printing. But there's a full set. Yeah. Yeah, I was carrying around some just 3.4 sections, and then now I'm all out of 3s. So that's good. It's good. Anyone want some chapter 2 notes while I'm at it? No? Chapter 6? No, no one. Okay. Doesn't hurt to ask. So the binomial, right? So the reason that I want to go through it officially is because there is a question on the final. It's a long answer question, and it is on the binomial. As I've kind of complained about before, I didn't write this final. It's kind of a common final, and so we're just gonna have to do what we can with it. You guys are more than prepared for it. I dare say that my final is a little bit harder, so you guys are all set up. But also, yeah, we need to go through the binomial. Okay. So a binomial situation is when we only have 2 possible outcomes, right? So think about proportions now, right? Because now we're talking categories, right? So a yes or a no, a boy or a girl is born, right? That kind of thing. So there's only 2 possible outcomes for your categories, right? So I'll add that here. For a categorical variable, so it's going to be very similar to proportions right? Probably our least favorite section because we had to check all those assumptions. Definitely my least favorite section to mark because of all the assumptions I have to check, but I will say that you guys did really well on checking the assumptions and just doing all the hypothesis testing and confidence intervals in general. So I'm really pleased with that. So you should be proud. So we've got two possible outcomes, right? Success, failure, pass, fail. That's the same thing. But success and failure in general, right, are just kind of, the success is whatever you're interested in, and the failure is whatever you're not interested in, right? So when we were talking about, okay, the proportion of boys being born, right, then a boy being born is a success, right? And then a girl being born is a failure, right? So in general, we talk about success, failure, yes, no questions, died, survived, right? Typically, kind of gruesomely, if we're looking at death rates or things like that, then a death would be a success just because that's what we're interested in, right? Did someone die from this disease, or did someone die from this, I don't know, medication? Let's talk about rats instead. Did this rat die from this medication that we're testing, right? And so that's the kind of thing that we want to model. And so each outcome is going to have some fixed probability, right? So this is taking us back to essentially chapter 2, where we talked about probability, right? And we'll see an example in just a second, but we'll talk about N trials. As far as what we talked about in chapter 2, right, we made tree diagrams and we said, okay, well, let's talk about the boy being born, girl being born, right? So in a family with 2 kids, right, you can either have a boy first or a girl first, right? And then you have your second child, and then your second set of branches, right, is your second child. So then you have a boy or a girl if you had a boy first, or if you had a girl first, you can have a boy or a girl, right? And so those are 2 trials, right, because you've got 2 layers of branches. The binomial lets us deal with N trials, okay? And we're going to talk about K as the number of successes. Okay. So for example, I don't know why I use this one. It's obviously not my example. I'm shooting hoops. I'm not sporty at all, so I don't shoot hoops. And I know the probability of each shot going in is 0.2. That's pretty good for me. If I shoot 3 times, what's the probability of exactly 1 success? Right, so if I shoot 3 times, right, first time it either goes in or it doesn't, right? So we have this binomial situation with only 2 possible outcomes, right? So I shoot once and it either goes in or it doesn't. That's the first part of our tree diagram, right, if we start there. And then I shoot again, either goes in or doesn't, depending on what happened initially. And then I shoot 3 times, and all of a sudden our tree diagram is already pretty large, right? Making it kind of hard to deal with. So we're going to solve this problem with a tree diagram and also with the binomial, and you'll see why we would use the binomial, because for even 3 trials, the tree diagram gets a little bit out of hand. Okay. I've got this tree diagram here, but there's actually overlap here, as you'll see. Let's see here, example 7. Let S be the shot goes in, or a success if you want. And then I'll just use the complement of S. Remember, the complement is just the opposite of it happening, which is going to denote that the shot doesn't go in. Taking us way back to tree diagrams, right? It's a little bit of a long time ago, but it's okay. So my first shot, thank you. My first shot, it either goes in or it doesn't. So this is my first shot. And then regardless of what happened initially, I'm gonna shoot again. And then, so I've got this second set of branches here where it doesn't matter what happened in the first shot, I can still have it go in or it doesn't go in. It goes in or it doesn't go in. So that's my second shot. Now it's time for my third shot. Now there's 4 possible outcomes that could have happened before it, right? And each of those gets a branch of 2 after. Right? So we've got 1, 2, 1, 2, 1, 2, 1, 2. Where it either goes in or it doesn't, it goes in or it doesn't, goes in or it doesn't, goes in or it doesn't. So this is my third shot. We're told that the probability of S is 0.2. Right? So the probability of S, I'll just put it up here, is 0.2. Making the probability of not S 0.8. You could show 1 minus 0.2, but it's okay. As far as P's and Q's, right, that's the same idea. So the probability of S is the probability of success, right, 0.2. So that would be your P in a proportion type of question, right? And then your Q would be 0.8, right? The probability of a failure, the probability that it doesn't go in is 0.8. So what's the question that we want to ask here? If I shoot 3 times, okay, what's the probability of exactly 1 success? So what I'm going to do is I'm going to trace down and just have a look at, okay, well, exactly 1 success. If my first shot was a success, then the only way that I could get exactly 1 is if I have this one and then I go down, I don't get it in and I don't get it in. Right? So that's the only branch that satisfies that criteria on the left-hand side. So if we do a little here, here, here. If I don't get it in on the first shot, then I can get it in on the second shot, but then I can't get it in on the third shot, right? Because we have to have exactly 1 success. Right? And so then we've got boom, boom, boom. Or if I don't get it in on the first shot, and then I don't get it in on the second shot, then I have to get it in on the third shot, right? Just to have exactly 1 success. So then I get boom, boom, boom. Oh, I guess I used H for a hit, I guess. I feel like S makes more sense. Oh well. So here, we've got our 3 options. We can look at the probability of S, not S, not S. The probability of not S, S, and then not S. and then the probability of not S, not S, S. Remember to get the probabilities at the end of each branch, we multiply down. Right? So we can take, okay, well, the probability of S was 0.2, probability of not S is 0.8, right? And so the probability of, I've got it over here. We've actually got the probability of S, not S, not S. Just to match the notes, I've got H instead, but it doesn't matter. Oh, and I know it was a while ago, but the little apostrophe is me forgetting to change it to a C. But they mean the same thing, the complement. So the probability of a success was 0.2 times not a success, 0.8 times 0.8. And so we get this probability of 0.128. If we look at all these combinations, right, because we've got just one success and two failures in each of these, it actually doesn't matter the order that we multiply them in, they're gonna have the same probability, right? 0.128, 0.128, 0.128. So if we add these up, right, because when we're saying, okay, exactly one success, then it can be this branch, or this branch, or this branch, right? So whenever we're saying or, we can just add those probabilities up. This, or this, or this, we just add up those probabilities. And so the probability of exactly one hit is the first one, or the second one, or the third one. And so we get 0.384 as our probability. That's how we would do it with a tree diagram. Here, I mean, yeah, once you've made it with the 3 levels, it's not that bad to deal with, right? But imagine if you had more than 2 possible outcomes, not for a binomial, but for another probability case, well, then it gets a little wonky. So for more than, I'd say, 3 trials, we're going to use the binomial. And the binomial is just going to make it easier to calculate these things because it's just a formula that we use. Okay. So we're going to talk about K as the number of successes. So in our case, right, we were looking for exactly 1 success in 3 trials, right? So then N is 3. So for the binomial, we've got this formula. The probability that X equals K, right, the number of successes. So the probability of K successes is N choose K, which might be a new function, so we'll talk about that. Okay, but N choose K times P, the probability of success to the power of K, the number of successes. And then we've seen this 1 minus P, right, which is the probability of a failure, right? We could replace this with Q if we wanted to the power of the number of failures, N minus K. So this I've got a list of what everything is. So where K is the number of successes, N is the number of trials, P is the probability of success, 1 minus P is often written as Q, as we've seen now, it's the probability of failure. And then N choose K, right? A lot of people want to make this a division, but it's actually not. It's just N choose K. And that's just going to figure out, okay, well, how many ways can I have exactly one success, right? In n trials, and I'm specifying, okay, I need to have one success, exactly one success. How many ways can that happen? And that's when we use this choose function. And so for us, right, we've got 3 trials and we're looking for exactly one success. So we're looking for 3, choose 1. We already know there's only 3 ways of getting exactly one success, right? Because we drew it out and we looked and we said, okay, well, there's these 3 options. But if you're using your calculator, and I mean, as long as you're using a, bless you, scientific calculator, it should have a choose function of some sort. If you're using this one, which isn't very likely, but possible, then it is above the plus sign. But it's usually one of the second functions, so it's kind of up above often. So make sure that you find it and that you know how to use your choose function. Okay. You guys got it? So we'll do a couple of just examples just to make sure that you have the choose function down. But for this calculator, you do the first number and then you hit the NCR button. And so this one here, it's usually NCR and capital CR that you're looking for. So choose, and then I have to hit 1. This one's kind of cryptic. It doesn't show you that it's doing anything until you hit equals, and then it tells you it's 3. 3 choose 1 is kind of hard because the answer is 3, so it's not very obvious that it's done anything, right? But if you try 10 choose 2, now we've got 10 trials, right? So imagine a tree diagram with 10 layers, okay? And you want to have exactly 2 successes. So you'd have to trace through all those layers to find how many ways we could have exactly 2 successes. And it turns out there's 45, right? So that seems like a lot of work. So if you do 10 choose 2, just make sure you get 45. So kind of get to know your calculator a little bit with the choose function. If you do 5 choose 5, it's not that surprising that it's 1, right? Because if you have 5 layers and every single layer has to be a success, then you only can go down one side of the tree. Is it working, Gabby? No. I'm confident there is one. We just need to find it. Yeah, because it's got the stats, so like it could be in one of these menus. We can find it later. I'm confident there is one. It's just a matter of finding it. We might have to Google it. Okay. So if you do 5 choose 5, you should get 1, right? There's only one way to have all successes or even all failures. If you do 100 choose 45, you should get scientific notation. And so I've got a note in the margin just saying, okay, be careful when you're seeing when your calculator is showing you scientific notation, because sometimes it's really subtle. Like on this one, I've got 6.144847 and then a little space and then 28. And that's all it's doing for scientific notation. And so what that's saying is 6.144,847 times 10 to the power of 28. That's huge, right? And so you definitely wouldn't want to do a tree diagram of that. And you'd hardly use your calculator, or can hardly pull it off, right? And so just be careful when you're seeing scientific notation, or at least be aware of what it looks like, right? So on this one, there's a little space. But if you try 100 choose 45, you will get scientific notation. And then 10 choose 7, why not? 120. So as far as our calculation goes, there's actually a typo here. I'm only looking for one success. So it should be 3 choose 1. Copy paste error. So what you have, we're looking for the probability of exactly one success, right? X equals to 1 is 3 choose 1. And then the probability of a success was 0.2 to the power of 1, right? One success. And then 1 minus 0.2, which is 0.8, to the power of 3 minus 1, which is 2 failures. Once you whittle this down, you get the same answer, right? 0.384. Any questions so far? Okay. So what's kind of cool and very similar to proportions is that we can actually find the mean and the standard deviation of a binomial distribution as long as some assumptions are met. Oh, assumptions, I know. Well, we can always calculate the mean and the standard deviation. I guess the fancy part is once we have mu and sigma, right, then we can calculate a z-score and we can find probabilities associated with binomial distributions. So once we have mu and sigma, we can use z equals x minus mu over sigma. Oops. And the z table to find probabilities. How we find the mean is just n times p. So your number of trials times the probability of a success, right? So I think intuitively we know that formula, right? Because if I tell you I'm tossing a coin 10 times, how many tails am I expecting to see? I'm expecting to see 5, right? Just because we know that the probability of flipping tails is 0.5, right? So 10 times 0.5. 10 is your number of trials times p, which is your number of successes, or your probability of success, 0.5. And so the mean, I think we've called it the expected value before, not too often, right? But just to start thinking about the mean is actually, it's the expected value. It's what we're expecting to see. And then the standard deviation is just the square root of n times p times q. Squish them all together under a square root. And of course, where q is 1 minus p. Which you already from proportions. Let's have a look at example 8. The S&P 500 index has a probability of 0.56 of increasing in any week. Assume the change in the index, change that little typo, in any given week is not influenced by whether it rose or fell in the previous week. That's a big assumption, right? But that's what we're going to assume in order to do this problem as a binomial, right? Because then we're just narrowing it down to, okay, did it go up or did it go down? Let X be the number of weeks among the next 5 weeks in which the index rises. So I'll add a page here so we can work through this. Example 8. Part A. How many possible outcomes are there each week? So each week, it can either increase or decrease. Since there are only 2 possible outcomes, we have a binomial distribution. Only 2 possible outcomes. We have a binomial distribution. Part B, identify what a success is in this case. Okay. So in this case, we're given the probability of it increasing is 0.56. So that means a success would be the stocks increasing, which I think we can all agree is a success overall. Well, generally. So a success in this case is the index increasing. Plus, part C, what are N and P in this case? So N is the number of trials. We're looking at 5 weeks, right? So that means we have 5 trials. Each week it can either go up or down, up or down, up or down, right? But we've got 5 shots, let's say. So 5, put in brackets, weeks. This is the number of trials. P, I think was 0.56. Yeah. Which is the probability of a success. It's also kind of how we determined what a success was in this case. You could easily swap it and say, well, the probability of a failure is 1 minus 0.56. And so then it decreasing would become a success if you use that probability instead. But for simplicity, we'll just use 0.56 and it increasing being a success because that's the most kind of reasonable thing to wrap our head around. Part D, what are are the possible values of x? So the possible values of x, Usually what we do, and you don't have to, you can just list them, but I'm going to use set notation, and so I'm going to say x equals, and then curly brackets. Again, you don't have to, but, and then we're just going to talk about, okay, well, what are the possible values of x? Well, x is the number of successes, right? So if we're looking at 5 weeks, in 5 weeks, I can have 0 successes. You don't want to forget about 0 successes. It can happen, right? That it's decreasing, 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 decreasing. That happens, right? So we could have 0 successes. We could have 1, 2, 3, 4, or 5. So 0, 1, 2, 3, 4, 5, and curly bracket. My left curly bracket's always better than my right curly bracket. I feel like my right curly bracket always has like a little face. So, any questions so far? Part E. What's the probability of the index increasing in more than 3, not including 3 of the weeks? So now, we want to know the probability that x equals, or x is greater than 3, right? Not including 3. So then I'm just going to say x is greater than 3. I'll make this more angled, maybe. Try to. The probability that x is more than 3, right? So not including 3, then you can either have 4 successes or 5 successes. So same idea here as when we're looking at the branches, right? We're going to say, well, that's the same as the probability that x equals 4 plus the probability that x equals 5. Oops. Four or 5 successes. Because remember, the formula can only handle the probability of exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, right? So what we're going to have to do if I'm asking for more than 3, not including 3, right, is just figure out those individual probabilities and calculate those and then add those up. So we need to find, or need to calculate these individually. Let's start with the probability that x equals 4. On your formula sheet, or just from the formulas in the notes, right, you've got the probability that x equals 4. Well, let's start, because it's our first one, by hand. In general, the probability that x equals k is n choose k times p to the k times 1 minus p to the n minus k. So then the probability that x equals 4 when n is 5, right? We had 5 trials, we're looking at 5 weeks. And so n is 5 and k is 4. Oops. The probability of a success was 0.56. So times 0.56 to the power of 4 times 1 minus 0.56 to the power of 5 minus 4. 5 choose 4 is 5. 0.56 to the power of 4 is 0.098344496. And then 1 minus 0.56 is 0.44 to the power of 1 is 0.44. Multiply those through, and I get 0.2163589112. That's the probability of exactly 4 weeks of the stocks increasing. Right? If the probability of an increase is 0.56 each week. Same idea. Now we find the probability that x equals 5. So the probability that x equals 5 is 5 choose 5 times 0.56 to the power of 5 times, I'll just skip to 0.44 to the power of 5 minus 5. 5 choose 5. We already decided was just 1, right? Because that's just following one of the outskirts of our tree diagram, essentially. So that's just 1. And then 0.56 to the power of 5 is 0.055073178. .44 to the power of 0. Anything to the power of 0 is just 1. So here we get 0.055073178 times 1 times 1. So those go away. It's going to be important to keep all your decimal places because sometimes the difference in the probabilities can be really, really small, especially if you have to subtract probabilities later. Right? That could happen, it won't, but right, when you're adding these probabilities, subtracting probabilities, then you need to make sure that you've got the most precise answer that you can have. Right? So do not round these probabilities. I guess I should have stored them. I didn't. Oops. But we're ready to calculate the probability that x is greater than 3, not equal to 3, is the probability that x equals 4 plus the probability that x equals 5, which was 0.2163589112 plus 0.055073178. 6358912 plus 0.055073178. I might have punched something in wrong, but I hope not. 0.2714320. And I would just leave the probability as that. So that's the probability of at least 3, not including 3, increases in 5 weeks. I guess more than 3. Any questions about that one? So then part F, what's the mean and standard deviation of this distribution? So the mean, oops. The mean is mu, which is n times p. N is 5 and p is 0.56. Right? So we're expecting 5 times 0.56, so 2.8 weeks of it increasing. This is one of those where you actually don't have to think about, okay, well, I can't have 2.8, so I'm going to round it. You're just going to keep the expected value is 2.8. So you just keep all your decimals. Just like with the average, we just keep all the decimal version if you prefer. The standard deviation is sigma, which is the square root of NPQ. So square root of 5 times 0.56 times 0.44. Yes, I think so. I'm pretty sure. I'm just thinking about the start, but yeah, pretty well. So it's going to be the square root of 1.232, and I'll give you guys the order and stuff on Monday and what to expect. So the square root of 1.232. So don't forget to take that square root. You get 1.109954954. Okay. Any questions about that? Oh. Then let's talk about the normal approximation to the binomial, because that's kind of the coolest thing about the binomial is that we can use a normal distribution to find probabilities, even if we've got these huge number of trials and huge number of successes that we're interested in. So we'll see an example here. First things first. As long as we have a large enough sample size, right, just the same as proportions, we can use the normal approximation to the binomial using mu as NP and sigma as the square root of NPQ, as long as, and these should look familiar, right, as long as n times p is greater than or equal to 10 and n times q is greater than or equal to 10. So as long as you're expecting at least 10 successes and at least 10 failures. So. Oh, we do it in parties, so it's okay. So these are the assumptions for using the normal approximation to the binomial. It's less than the proportions, but they're the same. Oops. So example 9. Suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O negative blood for a particular region this year. It estimates that it will collect blood from 32,000 donors, and only about 6% of people have O negative blood. Part A, what is a success in this case? Let's scroll down here. Start example 9. A success, in this case, right, is someone who has O negative blood, because we're told that only 6% have it, so then we know the probability of someone with O negative blood is 0.06, and so because that's the probability that we're given, that makes it a success. So it's O negative blood. Part B, what are N and P in this case? So N, the number of trials, is the 32,000 donors that we get, right? Because each of those either has O negative blood or they don't, right? Yes or no makes it a binomial. And so we've got 32,000 trials. That's huge. And our P is 0.06. N is 32,000 and P is 0.06. Part C. What is the mean and the standard deviation of this distribution? So the mean, mu, is NP, which is 32,000 times 0.06. 32,000 times 0.06, 1,920. That's how many donors we expect to have O negative blood, right? We know that because this is a sample, right? We could get more, we could get less, right? But that's around how many we're expecting to see. And sigma is the square root of NPQ. Square root of 32,000 times 0.06 times 0.94. We're going to need the square root of 1,804.8. So we've got a standard deviation of 42.48293775. I'll round it to 2 decimal places, 42.48. Okay. Part D, set up the formula for getting exactly 1,850 units of O negative blood from 32,000 donors. So this is just exactly 1,850 successes part. So the probability that X equals, I'll do the general one, K, is N choose K times P to the K times 1 minus P to the N minus K. So the probability that X equals 1850 is 32,000 choose 1,850 times 0.06 to the power of 1850 times 0.94 to the power of 32,000 minus 1850. 30,150. I only ask you to set them up, right? You don't have to, well, you can't do any calculations, right? You can try 32,000, choose 1,850. I get error 1. We blew it up. Because there's too many ways to have exactly 1,850 successes. Okay. So there, we've set it up. That's how you would calculate it. A computer obviously could, but we don't need to know the answer. Okay. So we will be able to find the answer to, well, E, check the assumptions, but F is what I was going for. So part E, check the assumptions for the normal approximation to the binomial. So, and then part F, how likely is Canadian Blood Services to meet its need of at least 1,850 units of O negative blood? So at least 1850, that's just 1850, 1851, 1852, right? All the way up to 32,000. They'd be thrilled, right? And so we're not going to do that by hand, right? That would be insane. And so first we're going to check the assumptions, but what you're going to find is that whenever you've got these kind of huge things that you're going to have to, or you feel like you're going to have to calculate, you can probably use the normal approximation, right? So the assumptions for the normal approximation is that we have to have at least 10 expected successes so N times P, which in our case is 32,000 times 0.06, which was 1920. Is greater than 10. And we have to have at least 10 expected failures N times Q, which is 32,000 times 0.94. 30,080 is also more than 10. So we're good to go. But as long as you calculate NP and NQ, make sure that they're greater than 10, then that's good. I'm just highlighting that it is at least 10 expected successes and at least 10 expected failures. So part F, they need at least 1,850 units of O negative blood. And so we want the probability that X is I'll say greater than or equal to 1,850. That's the probability they will meet their need for O negative blood. We already saw one of these, right, where we had to say, okay, well, what's the probability of the index increasing in more than 3 of the weeks out of 5, right? We had to find the probability of increasing in 4 weeks, and then the probability of it increasing in the 5 weeks, and then add those two up. Now we would have to go from 1850 all the way to 32,000. That feels a little crazy, right? But what we can do is we can use the normal approximation and say, okay, well, if I know the mean and the standard deviation, and I can say it follows a normal distribution, right, by the normal approximation, because the assumptions are satisfied. We've got the mean at 1920. Sigma, we said, was 42.48. On this normal distribution, right, 1850, we want to have somewhere here. We want at least 1850. And so this is the area that we want. This area is the probability that X is greater than or equal to 1850. We don't have any sample sizes or anything to deal with, right? So now to find this probability, we can use the Z table as long as we calculate Z is X minus mu over sigma. X in this case is the 1850. That's the point that we're interested in. Already looking at this graph, it's looking pretty good, right? That they're going to meet their need, more than 50% at least. So 1850 minus 1920 divided by 42.48. 1850 minus 1920. Negative 70 over 42.48. And negative 1.647834.275. We know how Z's behave, so we know we have to round to 2 decimal places, so negative 1.65. And now we can use the Z table. So using the Z table, we find the area to the left of Z equal to negative 1.65 is what? Negative 1.65.0495. So the area to the right is 1 minus 0.0495, which is 0.9505. Therefore, the probability that X is greater than or equal to 1850, it actually doesn't matter too if it's just greater than or equal to. So whichever one you prefer, is 0.9505. And that's the probability that they meet their need for at least 1,850 units of O negative blood. If you have a look for extra practice, of course, there's stuff posted on Moodle, but see assignment 3. I don't know, the last question. For extra practice, right? You don't have to hand it in. I've posted the solutions on Moodle. Solutions are on Moodle. And of course, you've got test 1 or C. Test number 1. Also the last question, I think, or I'm assuming. Which of course also has solutions posted on Moodle. Right. So try those. You don't have to hand anything in for the binomial, but definitely try them. Make sure that they're running smoothly for the final. Any questions? So now there's no more new material. Next week, we'll just do review. So on Monday, I'll tell you guys exactly kind of what to expect in terms of the types of questions, right? And then we'll start kind of reviewing some stuff. I'll see you guys on Monday. Thank you. Oh, and oh, sorry.
Did we already do like 3.4? Is it 3.4 or something? That first part we were doing.
Oh, it's because I wasn't here. I had to miss a day, and so that's why we went back and did it today.
Oh, okay.
For 3.4.
I figured you did it when I was like really sick and I was doing it at home.
It was for the bonus on test 1.
Okay.
Yeah.
Okay.
Yeah.
Thank you.
No worries. Yes. Gagandy. Thank you.